3.2. Differentiation rules. I understand quite a lot of you know quite a lot of this already, so I may go faster than normal. I'm guessing you don't want me to spend half an hour on that, for instance. Okay, we're going to be talking about the derivatives of constant and power functions. We're going to be talking about the derivatives of sums, differences, multiples, products, and quotients, and we'll talk about the derivatives of some transcendental functions. So let's go. I guess I'll write that. Derivative of a constant function. Okay, the derivative of any constant function is the zero constant function. That's it. Okay, you can prove that using limit laws and the definition of the derivative. Or you can realize that the graph of a constant function looks like that. It's flat everywhere. Its slope is zero everywhere. So there you go. Okay. Derivative of a constant function is zero everywhere. Okay, for the record, what are we doing in this lecture? We're trying to come up with general rules that you can get at through the definition of the derivative and limit laws and so on. And so these become general rules you can apply to find derivatives without having to go back to the definition of the derivative every time. Okay? The definition being the limit of the difference quotient. But if a function behaves badly at a point, we may have to look at limits of different quotients anyway. Okay. No questions about this? It's flat, derivative is zero. Okie dokie. Okay, power rule. For example, just this once, we'll go back to first principles. Suppose we want to differentiate x cubed. Okay? Go back to the definition. The derivative of f is the limit as h approaches 0 of f at x plus h minus f at x divided by h. And then I just use that. So the limit of x plus h cubed minus x cubed over h. I don't think we did an example quite like this, so I figured I'd show you this one. Okay. Now I expand this guy out. What do I got? X cubed plus 3x squared h plus 3xh squared plus h cubed minus x cubed all over h. Okay, how can you figure that out? You either expand this in the normal sort of way, or you use Pascal's triangle, or you use binomial coefficients, whatever works for you. Okay. What do we have now? X cubed cancels x cubed. And we're left with h times 3x squared plus 3xh plus h squared all over h. Okay. All right? All right. The limit doesn't care what happens at 0. So we can cancel these h's. And so we want the limit as h approaches 0 of just that. Okay? Yeah. It's possible. Yeah, it's possible. Likely or not, I have no idea, but it's definitely possible. Okay. Again, you can cancel here. You want the limit as h approaches 0, either by continuity with respect to h or limit laws. You wind up with those guys disappearing, and you're just left with 3x squared. Okay? So the derivative of x cubed with respect to x is 3x squared. If you have any questions about any step of that, let me know. And yes, I skipped steps this time. And if you want the x approaching a version of this kind of thing, let me know and I'll show you. Okay, you can use the same kind of approach for any power function where the exponent is a positive integer. Okay, you just do this expanding thing. But it turns out you can prove through other methods that this works for any power function. So there you go, there's the power rule. For any non-zero constant a, some people won't even say the non-zero, x to the a has derivative a times x to the a minus 1. Okay, I took the 3, brought it down in front, and decreased it to 2 upstairs. Okay? For example, we talked about the square root of x, which is x to the 1/2. So the derivative of that, bring the 1/2 downstairs, and upstairs reduce it by 1 to minus 1/2. Which is exactly what we got last time. Okay, another example. The derivative of the cube root of x squared, okay? That's just x to the 2/3. Bring this guy downstairs and reduce it by 1 upstairs. Okay? Easy as that. All right. And there's a picture for you. Okay, do all the checks on that. All the things we talked about. Look at the size of f prime and the steepness of f. Look at the sign of f prime. And whether tangents to f are positive slope or negative slope. So every time I show you a graph like this, do those checks. All right, and in particular, what have we got here? A cusp, yeah? And you'll see that the derivative fails to exist there in a special sort of way. Okay?
The cusp is the zeros or like...
Cusp is where you do this kind of thing.
Oh, okay.
Okay? There you go. Yeah, look at the last thing. Last class's note. Let me know if that doesn't make sense. Okay? We got a cusp, the derivative fails to exist in a particular sort of way. Okay, and so this thing is differentiable everywhere except 0. Questions? Okay. Cusp is an extreme corner. All right, new derivatives from old. Okay, we talked about how to get new functions from old by combining them algebraically or by composition. Now we're going to talk about how to differentiate combinations of functions. Okay, first, the constant multiple or scalar multiple rule. Okay, if a function f is differentiable on an interval I and c is a constant, then for all x in that interval, the derivative of the multiple of the function is just a multiple of the derivative of the function. Okay, which is how you'd want things to behave. You can prove this with the limit laws, or you can see it in a picture. If you stretch a function vertically by a factor c, the tangents get steepened by a factor c. So everything makes sense. Okay? Sum and difference rules. Okay, with the same hypotheses about being differentiable, the derivative of a sum is the sum of the derivatives, and the derivative of a difference is the difference of the derivatives. And like everything else, you can prove these things using the definition of the derivative, limit laws, etc. Okay? And this guy, along with the constant multiple rule, these guys make the differentiation operator what's called a linear operator, in case you're interested. Okay. And if you've got a sum of several functions, you can apply this thing several times in succession to be able to break up that derivative. All right. The rules we've learned so far allow us to differentiate any polynomial. So let's do a polynomial. Okay. Example. Five x cubed minus 3x plus 7. Okay. I've spelt it all out there. So especially if you're new to this, that's what you should be looking at. If you're more fluent with this thing, you may be able to do this all in one step. Okay, you want the derivative of this with respect to x. You can break it up using the sum and difference rules. And then for the derivative of this, you know it's 5 times the derivative of this by the constant multiple rule. And then you can use the power rule for this. Okay, so the first term, its derivative is 5 times 3x squared. This guy is minus 3 times 1, and the derivative of a constant is 0. So it's 15x squared minus 3. Okay, again, you can do it in that many steps, but as you become more fluent, you wouldn't even do this step. You just jump right to the final answer. Okay? Okay. Good? All right. This guy equals 0 at the plus minus the square root of 3 over 15. So plus minus the square root of 1/5. Equals 0 at x equals plus minus 1 over root 5. I hope. And if you look at the graph, that's exactly where the tangents are horizontal. Okay? We talked about high order derivatives. Let's do a few of those. The second derivative, 15 times 2x, that's 30x. The derivative of a constant is 0. Third derivative, 30 times the derivative of x. Derivative of x is 1, so it's just 30. And the derivative of a constant is 0. Yes?
Is that what linearization is?
Is what?
Linearization?
No. Linearization would be if you wanted to approximate this guy with a line. But this is just taking the derivative. Yeah, you'd use it. You'd use the derivative to do it, but this isn't that. Okay? The derivative of a constant is 0, so the fourth derivative and all subsequent derivatives are 0.
Would we need to know how to like sketch this? Like sketch the derivatives?
Soon. Sketch the derivatives.
I mean, no,
Well,
like sketch like the
sketch the function from the derivatives?
yeah, like I don't know how like the stuff over here.
Yeah.
Like,
The lines?
Yeah. How would we know like where for like
Where it's doing
F
this?
like yeah
Yeah, we'll talk about it.
F like incline is like bisecting it in the origin. Like how would we know that from like F?
Oh, we'll talk about sketches. Okay, this makes sense? Okay, those look like those? Okay. And do the usual checks on these things, right? The relationship between this and this is the same as the relationship between this and this is the same as the relationship between this and this. So do all those size and sign checks on the derivatives and the function itself, okay? Any questions? I don't know, I'm thinking this is not new to most of you, right? Is that, okay. Okay. If I make a mistake, you will definitely catch me, yes? Okay. All right. Again, look at graphs, make sure they make sense. Product rule. Okay. Shh. All right. The derivative of a product is not the product of the derivatives, okay? Which apparently is what Leibniz originally thought it was, but it isn't. Which he obviously figured out. Okay. If you want to prove to yourself that the derivative of a product is not the product of the derivatives, try differentiating something like x times 1. Okay? The derivative of that is 1. The derivative of this is 1. The derivative of this is 0. Okay? And 1 times 0 is not 1. Okay? So life's not that simple. Okay? So the point of that example is the derivative of the product is not the product of the derivatives. Okay? For limits, that was a rule, right? The limit of a product was the product of the limits. Okay? The reason this doesn't work here is that we're not talking about the limit of f and g, we're talking about the limit of the difference quotients involving f and g. Alright, so here we go. The derivative of f times g is the derivative of f times g plus the derivative of f. Sorry, okay. I just won't look at it. The derivative of f times g is the derivative of f times g plus f times the derivative of g. Okay? And if you make f some constant, okay, like 2, and you work this out, you'll see that this is consistent with the constant multiple rule. Okay? All right, quotient rule. Okay, as always, with the note that division by 0 is bad. The derivative of a quotient is not the quotient of the derivatives. Okay, the derivative of f divided by g is the derivative of f times g minus f times the derivative of g, all divided by the square of g. Okay? Don't forget that square on the bottom. Don't forget the minus sign, and make sure you get this order sorted out in whatever way seems right to you. Okay? It matters which way you subtract two things. Okay? So derivative of top times bottom minus top times derivative of bottom over bottom squared. Okay. And using the rules we have so far, we cannot differentiate any rational function. Okay, that's all for those rules. Any questions about the rules? I went quickly as promised, yes? No questions? All right. All right, give me a second. if you like to use prime notation for that sort of thing, that's cool too. Okay. Derivatives of some transcendental functions. Okay, let's start with exponential functions. Okay, so several times in the distant past, I told you that the instantaneous rate of change of an exponential function at a point is proportional to the size of the exponential function at that point. Okay, so for instance, I showed you this. Okay, if you can remember that far back. These are all exponential functions, and the slope here is proportional to the value of the function there. The slope here is proportional to the value of the function there, and similarly to the other guys. Okay? Okay, so that kind of thing we can now phrase as this. Nice. The derivative of an exponential function is proportional, and by all my exponentials are going to be positive as usual. Okay, the derivative of an exponential function is proportional to the value of the exponential function. Okay? And way back then, we talked about how the natural exponential function, the one with base e, is the only one where the constant of proportionality is 1. Okay? It's the only one where the slope of the tangent at a point is precisely equal to the value of the function at that point. Or in other words, e to the x is its own derivative. Okay? So what we talked about then, that's just it in terms of derivatives. Okay? Okay. There's stuff for you to write down. Or get off your computer. The exponential function is its own derivative. The natural exponential function is its own derivative. For a general base greater than 0, the constant of proportionality is ln b. Okay? So if I go back for just a second. Okay? How do I come up with these numbers? That's just ln 2. That's just ln 3. Okay? Okay, the fact that the natural exponential function is its own derivative is lucky. If you see it on the test, you're happy because you don't have to do any work. Fantastically useful and fantastically important. And I may get a chance to talk to you at some point about how the exponentials and the sinusoids are very, very beautifully and closely related. Okay. Warning. I said this before, I think. Do not confuse x to a constant with a constant to x. Okay? Here the variable is in the base, here the variable is in the exponent. Do not get these confused. Yeah.
So for e to the x, what if it was like e to the x squared? Would you still have to treat the derivative of 2 to the x?
E to the x all squared or e to the x squared?
Yeah, e to the x squared.
Yeah, chain rule. Yeah, this rule is exactly what it says, no more than that. Then for other stuff you have to use other rules. Okay? Please tell me if there's questions.
I mean, like, can you re-explain why, like, based on the graphs? Because I'm still kind of confused with, like, why e to the x is, like, when its derivatives, it's the same.
Why?
Yeah, like...
Because that's the special number that does it. If you look at the other ones, the constant proportionality at 2 is too low, the constant at 3 is too high. Okay, and it's a property of exponentials that you get that proportionality. Okay, so the constants of proportionality are too low and too high on the other side of this. There's one magical number where it's equal to 1,
Okay.
and that's e.
Okay.
And you can define e in this kind of way.
Alright.
So you can sort of define e by that property. Okay. Logarithmic functions. We'll talk about exponentials more, and we'll talk about that whole proportionality thing more. Logarithmic functions. Okay, we'll be able to prove later on that the derivative of ln x is 1 over x. For now, just accept it as fact. Okay, there are your graphs. Do the usual checks. For instance, the function, any tangent you draw to this guy is going to have positive slope. And surprise, surprise, the derivative is positive everywhere. Okay? The full graph of 1 over x is this. Okay? That's not the derivative of ln x. Okay? That would make no sense. Ln x isn't even defined here. Okay? Much less differentiable. Okay? So the derivative of ln x is 1 over x only for positive x. Okay? That makes sense? Okay, it'd be silly to talk about the derivative of something where the function doesn't even exist. Okay? Actually, I'll go back one. One more thing I wanted to say. Okay, the derivative of x squared is 2x. The derivative of x cubed is 3x squared. Okay? We're getting x to the something, and so on, okay? But with the power rule, there's no way of getting x to the minus 1. Okay? There's no way of getting a minus 1 upstairs with the power rule. Okay? So the answer to the question, okay? Sorry. The answer to the question, whose derivative is 1 over x, is this. Okay? Does that make sense? The power rule does not produce 1 over x. The thing that does is the natural logarithm part. Please tell me if there are questions. Sine and cosine functions. Always think in radians. Always have your calculators in radians, unless someone tells you otherwise. Not someone, us. Okay. I had it on that big sheet, so you can get out of that big sheet, that one big slide, or off of here, that the derivative of sine is cos, and the derivative of cos is minus sine. Don't forget that minus sign. Okay, and again, look at the pictures, everything should make sense, okay? Look where the function's flat, where the derivative is 0, and so on. Okay. If you wanted to prove this using the definition of the derivative, you need a few things. You need the addition identity, which we talked about, and one of the other things you need is this fact. The limit as x approaches 0 of sine x over x is 1. You don't need to write that down. But if you were going to prove that thing using the definition of the derivative, you would use that fact. Okay? Which we talked about at some point. That's why I'm bringing it up again. So it's an important thing. But not one that you need to know. Okay? 2 examples, unless there's questions. Alright. Let's move the derivative of tangent x. Okay? Alright. Tan is sine over cos. So the quotient rule seems reasonable. Okay. The derivative of the top, which is cos x. If I skip steps and you're confused, let me know now or later. Okay. The derivative of the top is cos x multiplied by the bottom, which is cos x, minus the top, which is sine x, times the derivative of the bottom, which is minus sine x. All divided by the square of the bottom, cos squared x. Something wonderful is about to happen, yeah? We've got cos squared x plus sine squared x, all divided by cos squared x. What's that top equal to? Excellent. 1 over cos squared x. What's 1 over cos x? Secant x. So this is secant squared x. It does come up a lot. Okay? So it's a quotient example. So a quick product example. If we want the derivative, no hands, x squared e to the x. Again, whenever you see an e to the x, you get happy. Okay, derivative of the first guy, which is 2x, times the second guy, which is e to the x, plus the first guy, which is x squared, times the derivative of e to the x, which is just e to the x again. And that's it, okay? And if you want it to be cute, you'd factor. Okay? Yep.
What happens if, like, instead of like our tan or any like sinusoidal function, what happens if the x is not like x though? Or is that for another like lesson?
It's for another lesson. Okay. It's for the other lesson. Yep.
On like the final, would you want us to factor a final explanation?
I don't think it matters. Honestly, as far as I'm concerned, when you get the answer, maybe leaving it is the best option. You don't waste time and you don't risk making a mistake, yeah? So unless we ask you to do something like that, then yeah, don't worry about it. Of course, factoring is sometimes very useful when you want to find out when something's zero and when it's positive and negative, right? So that's often when you want it. Okay? Okay, so we talked about a bunch of things, which is vague enough. We haven't talked about differentiating compositions and differentiating inverses. Okay? Composition is the job of the dreaded chain rule. And that's what we'll do next. Okay. Any questions about any of that? Wonderful. Next is the chain rule. I only said dreaded because you groaned last time I mentioned it. As far as I'm concerned, it's beautiful.